Okay, so today we're going to be looking at one of the most common structural materials. This lecture is really an introduction to concrete. What I want to do is to focus on some basic concepts. Right then, as you very well know, concrete is not found in nature the way we would find aluminum, nickel, or iron. Concrete is formed from combining water, a special cement, and rock. So the formula is Portland cement plus H2O plus rock equals hardened concrete plus energy or heat. Heat. Yes, and lots of it if your concrete structure is big. The heat and temperature variations in general can cause cracking problems. Now, a common mistake people make is to use the words cement and concrete interchangeably. It is important to remember that cement is only a component of concrete, and concrete is the structural material. The cement used in concrete is not used as a building material because it would be too expensive and not as strong as concrete. So when you see a parking garage, a driveway, a sidewalk, or a road, remember, it is made of concrete, not cement. And by the way, that funny-looking truck is a concrete mixer, not a cement mixer. But if cement is not concrete, then what is it? Cement is a general name for a material that binds other materials together. Yes, it is another name for glue. There are many materials which we would classify as cements, and they are usually identified with certain uses and can produce different types of concrete. The type of cement used to make the riding surface of some of our roads, blacktop, is called asphalt cement. It is known as a petroleum byproduct, and it binds rock into the road material we call asphaltic concrete. Turning to the next point, the structural concrete used in bridges and dams and other types of road surfaces is made from Portland cement. This cement binds the rock, also called aggregate, together to form concrete. But what is Portland cement? Well, Portland cement is a mixture of processed limestone, shale, and clays, which contain the following compounds: CaO, which is lime, Al2O3, which is alumina, and CiO2, which refers to silica, and iron oxides. Properties of the cement will vary depending on the relative amounts of these compounds. Okay, the next point is adding water to the dry cement starts a chemical reaction called hydration. While the mixture of cement, water, and rock is fluid, it can be poured into molds, also called formwork, of arbitrary shapes. This is a valuable property of concrete which allows us to build dams with the many different shapes which you saw in the history of dams, for instance. The compound gradually hardens into the desired final shape. Now, this is important. The water-to-cement ratio, or W/C, of the mixture has the most control over the final properties of the concrete. The water-to-cement ratio is the relative weight of the water of the cement in the mixture. The water-to-cement ratio is a design criterion for the engineer. Selection of a W/C ratio gives the engineer control over two opposing yet desirable properties: strength and workability. For instance, a mixture with a high W/C, or water-to-cement ratio, will be more workable than a mixture with a low W/C, or water-to-cement ratio. It will flow easier. But the less workable the mixture, the stronger the concrete will be. The engineer, therefore, must decide what ratio will give the best result for the given situation. Remember, this is not an entirely free choice, because the water-to-cement ratio needs to be about 0.25 to complete the hydration reaction. Typical values of W/C are between 0.35 and 0.40 because they give a good amount of workability without sacrificing a lot of strength. The other important component for strength is the aggregate, that is, the rock that is being bound by the hardened cement. Aggregate is what makes the difference between hardened cement and the structural material concrete. Why is aggregate important, you will ask? Well, aggregate increases the strength of concrete and is a fundamental economic factor because it takes up a large volume of the concrete and is much less expensive than an equivalent volume of cement, for instance. Next, to make very strong concrete requires a low W/C, or water to cement ratio, and strong aggregate. There might be thousands or millions of tons of cement and aggregate in a large dam. Another thing is finding the aggregate for the dam and transporting it and the cement to the dam sites are important societal factors. Typical composition by volume is cement 7 at 15%, water 14 at 21%, aggregate 60 to 80%. Here's a chance to make your own concrete. Notice that each component does not have a specific value, but rather a range of acceptable values. This means there are many ways to make concrete. Which combination of components gives the strongest concrete? Well, if an engineer designs a dam assuming certain strength concrete, how does he or she know that the concrete used was the strength wanted? These questions and more are answered by testing. But before we can break it, we need to make it. So read the recipe, get down to your local building supply store, and engineer some concrete.